And so this will be joint work with a few people who I'll mention along the way. And before start talking about things, just want to talk about a bit of motivation for those who maybe don't really study rational points. So one of the motivating things that we're going to ask is, how many primitive Pythagorean triples are there? So these are integer triples that share no common factor and satisfy a squared plus b squared equals c squared. So this is equivalent to asking, how many rational points are there in the curve x squared plus y squared equals 1, where x is a over c and y is b over c? So, so let x be this curve, and this curve is the defining equation for the unit circle. And in particular, this is a conic and can be visualized as so. So this is my rendition of this. So we have the circle, and I've sort of decorated a little bit. And this will become clear in a second what these decorations mean. So we can draw a line of variable slope t through a known point minus 1, 0. And we can just easily compute the second intersection point. And this leads to the following parameterization of the rational points of this conic. So you can see that the points are parameterized by this rational function in t, and we have this extra point minus 1, 0. So what we can conclude is that x, this conic, is isomorphic to p1, and the rational points can be parameterized by rational functions. Okay, great. So this is a nice simple example. It has some nice motivation. What happens when we bump up the exponents? Let's just bump up the exponent of the x coordinate. So the curve y squared equals x cubed plus 1 provably has finitely many rational solutions. So we're getting something different than what we saw before, just bumped up the exponent. But if I just tweak the coefficient, or sort of the coefficient, or the last term, this curve y squared equals x cubed plus 2 provably has infinitely many rational solutions. So just a slight tweaking of the equation changes the behavior of the solutions drastically. So what happens when I keep upping the exponent? Well, this curve, y squared equals x to the 5th plus 1, provably has finitely many rational solutions. And here are the 3 solutions. And then what about another curve? So we take this curve, y squared equals this following sextic, and you can prove that this actually has no rational solutions. Okay, so we've seen some behavior here. We've seen infinitely many points, finitely many points, and no points. So what we would like to do as arithmetic geometers and number theorists is come up with a geometric invariant which is controlling the arithmetic of curves. And this is sort of the credo of arithmetic geometers, that geometry determines arithmetic. So what is this invariant? So it's called the genus of a curve. I'm going to give you 3 equivalent definitions here. So let's let x over the complex numbers be a nice projective curve. So if you, so nice is actually a technical term from Bjorn Poonen, and it means, for those who know about the definitions, a smooth, projective, geometrically integral curve. For now, let's just think about a projective curve. So it lives in projective space. So the genus is an integer from 0 to some number, and it can be defined in the following 3 equivalent ways. So the first one is the topological genus. So we look at the c-value points of our curve. This will give us a compact Riemann surface. Here's where the projective assumption is coming in. And this gives us a G-hold torus. So we have a picture of a genus 0 curve, a Riemann sphere, genus 1, a donut, genus 2, 2-hold donut. So are there other notions? How do we define sort of the genus in a more geometric way, maybe? We can define it as the dimension of the space of holomorphic one-forms, and this is called the geometric genus. And we also can define it as the dimension of the sheaf cohomology group H1x O of x. This is called the arithmetic genus. So this is giving us 3 ways to define the genus. And the latter 2 give us a way to define it over a field that isn't the complex numbers. So let's look at how the arithmetic of these genus G curves behaves. So let's start genus 0. So let's let X be a genus 0 curve over the rationals. Every such curve can be written as a conic in P2, given by the equation ax squared plus by squared equals cz squared, where a, b, and c are square-free pairwise relatively. And there's actually a very simple test to determine whether X has a Q rational point. In particular, X has a Q rational point if and only if it has a real point and it has a QP point for all primes P. And this is an instance of the Hoeij principle, which I think was mentioned in one of the lightning talks by Andre, I believe. So this is very nice, and you might think, okay, well, determining a QP point, well, this is quite straightforward. You can reduce mod P and use Hensel's lemma to lift solutions to QP. So this is very, very easy. And in particular, one can show, like we did with the conic x squared plus y squared equals 1, that if X has a rational point, then X has infinitely many points. So in particular, you either, if you have a point, you have infinitely many points, but of course, there could be no points. Okay, so moving up to genus 1 curves. So we've seen this in the lightning talks as well. But here's a nice example that I think is very good. So Selmer, I don't have the exact date, but it was quite a while ago, constructed a genus 1 curve, 3x cubed plus 4y cubed plus 5z cubed equals 0. And this curve has no Q rational point, but has real and QP points for every prime P. So this is a genus 1 curve with no rational point, but it has local points everywhere. So this example tells us that A, genus 1 curves might not have a point, and B, the Hoeij principle doesn't hold for genus 1 curves. And so one of the main objects of this talk will be an elliptic curve. So a nice curve of genus 1, which has a distinguished K rational point, is called an elliptic curve. Because we're going to be working over number fields and fields of characteristic 0, an elliptic curve has an affine equation given by y squared is equal to f of x, where f of x is some separable cubic. And if you have studied elliptic curves before, you know that the rational points of an elliptic curve have a very nice structure. In particular, they form an abelian group. First, and so we define the relations by saying that 3 points sum to this distinguished point infinity if and only if they are collinear. And now the non-trivial theorem, which is proved, I think, in most textbooks on elliptic curves, for example, Silverman and Tate's book, is the following theorem of Mordell and Weil, which says that the K rational points of E actually form a finitely generated abelian group. So we saw this in Hansen's talk, and this will be something that we'll talk about later on. But this is very nice. This tells us that we have a lot of structure and control over the rational points in an elliptic curve. But we don't really understand the rank too much, but that's for a different talk. So moving on, what about curves of genus greater than or equal to 2? Well, we have this amazing theorem, first proved by Faltings, and then another proof was given by Voida, which was simplified a bit by Bombieri, and recently there's been another proof by Lawrence and Venkatesh. So it's, if you can prove the same theorem 4 times over, you're doing a good job. So it says that if we have a nice curve of genus G greater than or equal to 2, then the set of K rational points is finite and might be empty. So we've seen a lot of different behavior, and so we can summarize this in the following table. So we have on the left-hand column the genus. So when the genus is 0, the behavior of the rational points, it's either empty or infinite. And there's another geometric birational invariant called the Kadir dimension, which comes into play. And so the Kadir dimension of a genus 0 curve is minus infinity. It's what's called a Fano variety. We have a genus 1 curve. We've seen that the behavior of rational points can be empty, finite, or infinite. And here the Kadir dimension is equal to 0, and these are Calabi-Yau manifolds or varieties. And when the genus is greater than or equal to 2, the rational points can either be empty or finite. And here, the Kodaira dimension is equal to 1. And this is what's called a variety of general type. So I won't define what the Kodaira dimension is, but this is a number attached to a variety of dimension n that goes from -infinity to n. And it sort of gives us a way to classify varieties. And so one of the principles or one of the main conjectures in arithmetic geometry is that varieties of general type should have a sparse set of rational points. More precisely, the rational points should not be Zariski dense. This is what Lang has conjectured. And so in the dimension 1 case, this is what this above theorem of Falting's, Voida, Bombieri, and Lawrence and Venkatesh is proving. So following Falting's theorem, we have these motivating questions which are going to guide what we're going to talk about for the rest of the talk. So the first one is, can we provably determine all of the rational points on a higher genus curve? So I highlighted the word provably here because you can, of course, go into Magma or Sage, whatever your favorite computer algebra program is, define the curve and search in a box for rational points. And so you might say, I found no points, but that doesn't prove that there are no points. You might find some, and that doesn't prove that those are all the points. So are there techniques that tell us these are all of the rational points or there aren't any rational points? The next question is, how does this finite quantity vary in families of curves? So for example, hyperelliptic curves, which we'll talk about later. Third is related to algebraic points. So if we take an integer d, which is greater than or equal to 2, is the set of degree d points. So these are points living in the algebraic closure where the coordinates live over some extension of degree d. So is the set of degree d points finite? And if so, again, can we provably determine all of the degree d points? So the next results that I'm going to talk about are related to all of these questions. But before I do that, I took this from Robert Lemke-Oliver's slide. I want to pause for any questions that there might be. Okay, so I don't see anything in the chat, so I will continue. So let's talk about odd hyperelliptic curves. So here's the technical term, the technical definition. So we're going to have C over Q, a genus G greater than or equal to 1, hyperelliptic curve with a marked rational Weierstrass point infinity. Equivalently, this means that C has the affine equation y squared is equal to f of x, which is equal to x to the 2g plus 1 plus a2 x to the 2g minus 1, and so on, where f of x is separable. And we call these odd hyperelliptic curves. So one thing to note here is that we call them odd because the exponent is odd. And also when you plug in g is equal to 1, you get the affine equation for an elliptic curve that was mentioned before. And so we can impose a sort of minimal unique Weierstrass model, which is a model for the curve or an equation where the coefficients satisfy certain divisibility conditions related to primes. And this gives us a way, since we have this unique minimal Weierstrass model, we can order the hyperelliptic curves, which gives us a way to study them in a family. So we say that for an odd hyperelliptic curve, the height of C is the max of the absolute value of the coefficients, where for the coefficient ai, we raise that to the power 1 over I. And this is really because you consider things in kind of a weighted projective space, but we take this height for the unique minimal Weierstrass equation. So whenever we talk about hyperelliptic curves ordered by height, this is the height we're referring to. So rational points on odd hyperelliptic curves. So let's let math-cal f of g denote the Q isomorphism classes of genus G odd hyperelliptic curves. And there's an amazing theorem of Poonen and Scholl, which says that if we fix g greater than or equal to 3, when these genus G odd hyperelliptic curves are ordered by height, a positive proportion of these curves only have one rational point, namely the marked rational Weierstrass point that we talked about. And you can phrase this in a more precise manner by saying this lim imp over the number of curves of height less than x, which satisfy this condition over the number of curves of height x, is positive. And so they actually prove more. They say that this proportion will tend to 1 when the genus goes to infinity. So if you've heard of this result, the colloquial way to say this is that most odd hyperelliptic curves have 1 point. So this is an amazing theorem because it's studying how rational points vary in families, but it's also giving us a precise control over the rational points. It's saying there's only 1. So this is a really amazing result, and this was the motivation for the work that Joseph Gunther and I did, which I'm going to mention soon. So before we go to higher degree points, I want to just mention that there's related results of Shankar-Wang for even hyperelliptic curves, so where the defining equation is even, Bhargava for the family of all hyperelliptic curves, and there's work of Algebraic studying the average number of points on genus 2 hyperelliptic curves. So let's move away from families of curves and let's talk about algebraic points. So we're going to focus on quadratic points because this is a very informative example. So if we have a hyperelliptic curve, y squared is equal to f of x, this is equivalent. It means that the curve emits a 2-to-1 map to P1. So and this implies that there are actually infinitely many quadratic points. So you might argue that a hyperelliptic curve actually admits a 2-to-1 map to a conic, but I'm going to assume that conic has a point, so it is a P1, so no problems there, just in case my advisor is watching. And that says, and so we have infinitely many quadratic points, and here they are. You basically take your favorite rational number, you plug it into f of x, and you take plus or minus the square root, and these give quadratic points. And these are what we call expected quadratic points. So the thing to note here is that the x-coordinate is rational and the y-coordinate is irrational. Okay, so let's do another example. So we have this genus 4 hyperelliptic curve, y squared is equal to x to the 9 plus x cubed minus 1. And so this has the expected points. So I just plugged in 0, minus 1, and 2. We get these points. But there's also some interesting unexpected points which happen. So we get unexpected quadratic points. For example, if you plug in I, you can't remember where the plus and minus refers to off the top of my head, but you can see that the x-coordinate in these examples is irrational, and so is the y-coordinate. And they both live in the same field. So the difference between these expected and unexpected points is that the x-coordinate is living in an irrational field, and the y-coordinate is living in that same irrational field. Okay. So that's great. So now you can ask, okay, well, so we had infinitely many expected points. What about these unexpected points? And a theorem of faultings says that if we have a hyperelliptic curve of genus greater than or equal to 4, then there are finitely many unexpected quadratic points. So the thing to note here is that there's a condition on the genus, and once the genus kicks in, we have finitely many unexpected quadratic points. Yes, so these are also called exceptional points, sporadic points. We as a community have not decided on what to actually call them, but they all sort of mean the same thing, but yeah, it's a great point. So great, so now when the genus is large enough, we have finitely many. And just to give an example of how classifying these points can be rather difficult, there's a nice example of Samir Siksek. And he says, consider this genus 3 hyperelliptic curve. This has exactly 9 pairs of unexpected points. So I'm going to list 3 of them for you. So we have the first one, I think everyone could find that one. And the first and the second one, everyone can find that one. But this last one is pretty mysterious. Kind of no idea where it comes from. And also, I couldn't even fit its conjugate on the slide. So it's sort of telling us that these unexpected quadratic points are pretty difficult to classify explicitly. And they're also kind of hard to understand where they're coming from. Okay. So we've talked about quadratic points. What about cubic points? Well, the geometry of a hyperelliptic curve doesn't a priori impose any cubic points unless it is trigonal or trielliptic. And that means that C admits a 3-to-1 map to P1, or respectively a 3-to-1 map to an elliptic curve. And similar to Falting's previous theorem, there's work of Abramovich and Harris, which says that a hyperelliptic curve of genus G greater than or equal to 6 has finitely many cubic points. We've seen these two prototypical examples here. So now I can state the results that Joseph and I were able to prove. So we proved, and work with Joseph Gunther, we say, suppose some technical assumption holds, which I'll talk about in a second. For each G greater than 2, a positive proportion of odd height Q, when ordered by height, have at most 24 quadratic points not obtained from pulling back points of P1 of Q. So at most 24 unexpected quadratic points. And we also prove another result for cubic points that says for each G greater than 3, a positive proportion of odd hyperelliptic curves when ordered by height have at most 114 cubic points. And we prove a more general result where we say, let's let D be a positive integer, suppose a technical assumption holds. If D is odd, then there exists some number B of D such that for each G greater than D, a positive proportion of odd hyperelliptic curves have at most B of D points of degree D. And if D is even, there exists a number B of D such that for each G greater than D, a positive proportion of odd hyperelliptic curves have at most B of D points of degree D not obtained from pulling back degree D over 2 points on P1. And so when you plug in D is equal to 2, when D is equal to 2, you get our result for B of 2 is equal to 24, and B of 3 is equal to 114. So this is giving us some, okay, so do you think the number 24 is optimal? That's a great question. So with the techniques that Joseph and I used, if there was a way that we knew that a positive proportion of odd hyperelliptic curves had rank 0, we could get this down to 0. With our methods, the 24 is about as good as it's going to get. The 114 is definitely not as good as it could be, but it's a great question. Okay, so some remarks. We can take B of 1 is equal to 1 unconditionally, and this is by results of Poonen and Stoll and Romano and Thorne. Here is what the B of D actually comes out to be through the wash. So it's not very pretty, but it only involves D, which is great, what we wanted to do. So we had this condition in our theorem that the genus was greater than D, and this refers to the fact that the symmetric product is of general type. I'm going to talk about the symmetric product later on, but remember this philosophy that when the variety is of general type, there shouldn't be, we should expect a sparse set of rational points. So this is part of the reason why we have this assumption. And one can view our result as bounding rational points in a family of higher dimensional varieties, which do have some rational points. So the reason why we have some rational points is because we always have this marked rational Weierstrass point. And finally, this technical condition comes from tropical geometry. And roughly it states that the tropicalization of an isolated point is an isolated point in the tropicalization. And if people would like to know more about that, I can explain when the time comes. So ingredients of proof. So this formula, yes, the formula for B of D works for D even and odd. We don't have to break it up into two different proofs. That's a great question. Why we don't have to break it up differently later on. So some notation, C over Q be our odd hyperelliptic curve of genus greater than or equal to 2. Jac of C denote the Jacobian, and R is going to be the Morrow-Bay rank. So this is the rank of the Q points of the Jacobian, which is also a finitely generated abelian group, again by the theorem of Bay. And so the ingredients are, we use some theorems concerning the arithmetic and geometry of hyperelliptic Jacobians. For example, we have Falting's theorem about rational points on subvarieties of abelian varieties. We have work of Bargava and Gross on the average rank of hyperelliptic Jacobians. And we use a criterion of Zarin, which says that when the Jacobian of a hyperelliptic curve will be geometrically simple, or in other words, when it won't contain abelian subvarieties. And then the technique we use to get our bounds, and in particular explicit bounds, is refinement of the symmetric power Chabauty-Coleman method, which was pioneered by Samir Siksak and Jennifer Park. And so what I'm going to talk about now is the method of Chabauty and Coleman, which gives a way to provably determine rational points on certain types of curves. So 40 years before Falting's theorem, Chabauty proved that if we have a higher genus curve and that the rank is less than or equal to the genus minus 1, then the rational points on the curve are finite. Now, of course, every curve does not have rank less than or equal to g minus 1, but this is still a positive result. And around the time when Faltings proved his theorem, Coleman, using the theory of p-adic integration, was able to make this Chabauty's theorem effective. And so he says the same assumptions, and we suppose that p is a prime of good reduction and that the rank is less than or equal to g minus 1, and the number of rational points on the curve is bounded above by the number of fp points plus 2g minus 2. And so for those, the 2g minus 2 is should remind you of Riemann-Roch, and that's exactly what's happening there. And so later, Stoll was able to further improve this by removing the Riemann-Roch term and replacing this with a 2r. So his result says that the number of rational points is less than or equal to the number of fp points plus 2 times the rank. So this is so Stoll's theorem is great because what we expect is that when the rank of the Mordell-Weil group of the Jacobian is small, we should get less rational points. And that's exactly what Stoll's theorem is saying. So how does this go? We use p-adic integration. And so we can define an integration pairing. We take one forms on the curve and a divisor on the Jacobian, and we can integrate them. And so for any one form, we can define locally analytic functions on the CP points of our curve. So we take a point and we integrate along the divisor p minus infinity. And so how do you compute this? Well, it's actually very nice in practice. So locally on C of CP, that is on a p-adic disk with center P, we can express these f omega as convergent one variable power series. And so the way you should think about this is the omega, because we're working on a p-adic disk, will be exact, so it can be written as a power series, and then this f omega is just given by formal anti-differentiation. And so the Chabauty-Coleman method is fueled by this rank assumption, and when the rank is less than or equal to g minus 1, there exists a space of one forms called lambda of c, where when we integrate omega against the divisor on the q points of the Jacobian, we get 0. So these are what are called annihilating differentials. And in particular, the integrals of these one forms in lambda of c will vanish on the rational points of our curve. So if we want to actually bound the rational points, we need to bound the zeros of a locally analytic function. And this can be done using Newton polygons. And we have this p-adic Rolle's theorem of Coleman, which says that the number of zeros in a residue disk, or you should think about this as a p-adic disk, is 1 plus np, where np is the number of zeros of this one form in a disk. So in other words, what this is saying is the number of zeros of an integral is equal to 1 plus the number of zeros of the derivative. So kind of a Rolle's theorem type thing. And then Riemann-Roch will tell us that, well, when we sum over all the p, we can bound the np by 2g minus 2, because this Riemann-Roch gives us number of zeros of a one form. And then putting this all together, we get Coleman's bound, where we have the sum over 1 plus np, so we get the number of fp points plus 2g minus 2. And so what Stoll did was he replaced the Riemann-Roch term with 2r. So now we have that the sum of the np is less than or equal to 2r, and then we get Stoll's bound in the same way. So we have the we have 1 plus np is less than or equal to number of fp points plus 2r. The method that Joseph and I use is basically the d-dimensional version of this. So for a one form, we define this capital F omega d on the d-fold product of our curve, where we take a d tuple of points and we integrate against p1 plus p of d minus d infinity. And so again, if we have a one form in lambda of c and p1 through pd is a d tuple of conjugate degree d points, then this fd omega will vanish on this d tuple because p1 plus pd minus d infinity is a q-rational point of the Jacobian. And like before, locally on this d-fold product, that is on a p-adic polydisk, we can expand this fd omega as a convergent d-variable pure power series. So the term pure here refers to the fact that there are no mixed terms. When we write this sum, we only have a summation of T1 plus some summation of T2 plus up to the summation of T. And this allows for us to have better control of the Newton polygons. And so when the rank is sufficiently small, namely when the rank is less than or equal to G minus D, we can pick D linearly independent one forms, omega 1 through omega D, such that the common zeros of these fd omega 1 through omega d contain all d tuples of conjugate degree d points. Now this is great, but as we saw, this can introduce a problem, namely that the zero locus of these integrals is positive dimensional, coming from the infinitely many expected points. And it's hard to control these positive dimensional components. So what Joseph and I do is, well, we found a way around this, and we prove that when the rank is sufficiently small, namely less than or equal to 1, we prove that the expected points only come from positive dimensional components. So this is really, this allows us to really control things because we actually know where these expected points are lying, which is really useful. And then once we know this, we can use some rigid analytic deformations to deform the remaining positive dimensional components to zero dimensional components. So the thing here is we keep the same zero dimensional components, but we're just going to introduce more of them. But this will make our count worse in some sense, but that's a trade-off that we have to make. And then we use tropical geometry arguments, in particular mixed volumes, which you should think of as a way to measure the size of a polytope to bound these zero dimensional components. So similar to how Coleman used Newton polygons to bound the zeros of p-adic integrals, we use mixed volumes to bound the zeros or the zero dimensional components of D variable power series. So that's kind of the yoga that's going on here. And so, so that was sort of the first part of the talk, and I'm gonna, as it says, pause for questions. And up next will be some results about torsion. Okay, and so going back to, there's a question in the chat about whether we break it into two cases. This is why we don't have to break it up into two cases, because when we prove this rank result, we know where the expected points will lie. And so when D is odd, there really aren't expected points. There really aren't expected points, but when D is even, there are expected points, but we sort of remove them from the situation. So that's why we don't have to break it up into different cases. Okay, so moving on to talk about some torsion for elliptic curves over cubic number fields. And this will be related to algebraic points on curves, as we're going to see shortly. And so as Hansen said, he sort of gave a nice appetizer for this talk. So I'm going to recall some of the stuff that Hansen talked about. So if you have an elliptic curve over a number field, the Morrow theorem says that the k rational points form a finitely generated abelian group. R is going to be the algebraic rank, and ek tors will be the torsion subgroup of the elliptic curve. And so the problem we're interested in is saying, if we fix some d greater than or equal to 1, can we classify which finite groups appear as the torsion subgroup for k over q, a degree d number field? And a follow-up question is to ask which of these groups occur infinitely often, namely for infinitely many J invariants of elliptic curves. So we have this wonderful theorem of Mazur, which says that if we have an elliptic curve over the rationals, then E of Q torus is isomorphic to one of the following 15 groups, and each of these groups appear infinitely often. So this is an amazing result. And how does Mazur go about proving such a result? Well, he studies rational points on these things called modular curves. So just set some notation. Let's let y1 of n denote the curve, which parameterizes tuples e comma p, where p is a point of exact order n on an elliptic curve. y1 m comma n, where m divides n, be the curve parameterizing elliptic curves, where the torsion subgroup contains z mod mz, some z mod nz. And let's let x1 of n and x1 of m comma n be the smooth compactifications of these curves. So when you talk, yeah, these points will have some points which don't actually have a certain moduli interpretation, which are called cuspidal points, and these will be very useful to us later on. So we can restate Mazur's theorem as follows. It says that y1 of n, and x1 of n and x1 of 2 comma 2n are isomorphic to p1 for exactly the n which appear in Mazur's theorem. And if the genus of these modular curves is greater than 0, then the rational points only consist of cusps. So they don't correspond to elliptic curves with this prescribed, with these prescribed torsion conditions. So in some sense, the simplest thing that can happen for these modular curves does happen, but this should illustrate to you how amazing this result of Mazur is. I mean, he basically classified rational points on all of these modular curves. I mean, we talked about how it's hard to classify the points on one curve, but he did it for all of the modular curves, which is quite amazing. Yeah. So great. So what about the quadratic case? So when we go to degree 2 number fields. So this was joint work that was done by a few different authors, and it resulted in the theorem of Kamieni, Kenku, Momose. And it says that if we have an elliptic curve over a quadratic number field, then the torsion subgroup is isomorphic to one of the following 26 groups. And each of these groups appears infinitely often. So one thing to note here is that when we had rational torsion, we only were getting subgroups z mod nz and z mod 2z plus z mod 2 nz. And here we have some 3z and some 4z appearing. And this is due to the Weil pairing and the fact that we're working with some quadratic number fields. But one remark, which ties it into the algebraic points we were talking about before, is that the corresponding modular curves in this situation all have genus less than or equal to 2. In particular, they're all hyperelliptic. I mean, except for the ones that are genus 0. But I guess that's fine too. Never mind. This basically, as we saw before, this will guarantee that there are actually infinitely many quadratic points. So the geometry of these modular curves is telling us something about the torsion subgroups appearing, and in particular, how often they're appearing. So what I want to talk about is the cubic case, but we need to get a little bit more information. So Morrow proved the following uniform boundedness theorem, which says that for every integer d greater than equal to 1, there is some constant such that for all number fields of degree d and all elliptic curves, the torsion is bounded by n of d. So this is telling us that the theorem of the problem of classifying torsion over number fields is tractable, and there's some finite number where it can't be larger than this. So for cubic number fields, there was work of June, Kim, and Schweitzer, which says that over a cubic number field, the groups which arise infinitely often come from the following 25 groups. And 10 years later, Philip Nyman found an example of an elliptic curve E over Q whose torsion subgroup over the totally real subfield of Q zeta 9, which is a cubic field, is Z mod 21Z. And he proved that, and this is the only elliptic curve which has Z mod 21Z torsion over a cubic number field. So we have the following 25 groups which appear infinitely often, and we have this one group which is occurring only once. So people conjectured whether this was all that was happening. And in fact, the work the theorem that Martin Derickx, Anastasia Etropolski, Mark van Hoeij, myself, and David Zureick-Brown can prove is that, yes, in fact, this is true. So over a cubic number field, the torsion subgroup is isomorphic to one of the following 26 groups. And furthermore, every torsion subgroup appears infinitely often except for Z mod 21Z. So I want to talk a little bit about the proof of this theorem. And before that, I need to set some notation. So let's let x over q be our nice curve, and Jac of x denotes Jacobian. As Hansen talked about, we can define the gonality of this curve as the minimal degree among all finite morphisms of x to p1 of q. And for a positive integer g, we define the d-symmetric power of x to be the d-fold product modulo the symmetric group on d letters. And so the q points of the symmetric power correspond to effective q rational divisors of degree d. And in particular, if we have a point of degree d on the curve, this will give rise to an effective degree d divisor, and thus a rational point of this symmetric product. So this tells us that if we want to study rational or higher degree points, we should really be studying rational points on the symmetric power. Now the trade-off is we have to study rational points on now a higher dimensional variety. But that's life. So, and if the symmetric power is, the rational points are non-empty, then a fixed Q rational divisor D of degree D will give an Abel-Jacobi map where it goes from the D symmetric power to the Jacobian, and where we take D prime to D prime minus D. So this will give a degree 0 divisor. So the strategy of our proof is, by work of Perron, Momose, Wang, Bruin, Nyman, it suffices to determine the cubic points on the following modular curves. So x1 of n1 for n1 as follows. And so we break this up into two cases. So the first thing we do is we provably determine the ranks of the Jacobians for these curves. And we find that all but two of them have rank 0, which is great. So when the rank is 0, we explicitly compute the finitely many preimages of an Abel-Jacobi map. And this is really great because it says the Jacobian is torsion. However, the torsion on these Jacobians gets really, really large. Like for some values, it's like the order is up to like 45,000 or something. And we want to actually have explicit generators of this. So one of the things we do for this is we use these modular units that Hansen talked about in his talk. But I'll say a little bit about this in a few minutes. And then for the positive rank cases, for n1 is equal to 65 and 121, we use a modified form of Kamiani's criterion to verify that a morphism from the symmetric cube to a rank 0 quotient of this Jacobian is a formal immersion. So I won't define what these formal immersions are, but these are techniques that Mazur and Morrow used in their proofs, and they're incredibly useful tools for studying higher degree points on curves. Yeah. So so we were going through, and we had a large list of these modular Jacobians whose points we wanted to classify. And at some point, I think David was the one who kind of got this crazy idea and said, let's just classify all of the modular, or all of the Jacobians of these modular curves with rank 0. So here we go. Let's let S0 be the following set. So the rank of J naught of n of Q is 0 if and only if n is in this S naught. And the rank of J1 of n of Q is 0 if and only if n is in S naught without these points in here. So if you've ever been looking at a Jacobian of a modular curve and wondered whether it has rank 0, here you go. Here's a list of all of them. So this was nice. And so we have these rank 0 modular Jacobians, and we have these rank 1 modular Jacobians. And so I said that we just compute the finitely many preimages, but we can't always do that in practice because sometimes we don't actually know what the torsion on these Jacobians are. We can get upper bounds using local methods, but it's hard sometimes to prove that this is all of the torsion. So we use a lot of different techniques, and a lot of curves require different techniques. And so here is a table which is summarizing the methods, the levels that we consider, the genera of the curves, and the methods. So you see there's most of the curves have higher genus. There's some terms called saturated sieving. A lot of times we do a direct analysis. Sometimes we use a sieving technique. And so sieving here is referring to the Mordell-Weil sieve. And so as you can see, the genera of these modular curves is quite large. For example, we work directly on a genus 10 curve. And the level x1 of 121 is a genus 526 curve. And so we're able to actually compute the cubic points on a genus 526 curve, which is pretty nice. And so the way that we do this is we work on curves of smaller genera, in which I've listed here. And so one thing to note here is that the genera of these curves is always greater than or equal to 3. And so the reason for this is if the curve has genus 2, then it will actually have infinitely many cubic points. So we're not actually going to be able to use those to determine the cubic points on these higher genus curves. And so all of these genus 3 curves are actually hyperelliptic. And the problem is if you have a curve of genus less than or equal to 4, it's either hyperelliptic or trigonal. So if we found a lot of genus 4 non-hyperelliptic curves, however, we can't use those because they contain infinitely many cubic points. So you have to get pretty lucky for these sort of curves that you're working on. And so that's why some of these other ones we have the genera of the curve is not applicable, because there wasn't sort of an intermediate hyperelliptic curve that we could work on. And so, so a lot of like the examples of 26, 28 were actually some of the more difficult ones because we really just had to work on these genus 10 curves and just go from there. So as a last thing, I want to give a sort of detailed example of what's happening in kind of the first case that we did. So we have x1 of 21, which is a genus 5 curve, and it has gonality 4. And so we have the following known points. We have 6 rational cusps, not cups, sorry. 2 quadratic cusps, the 2 cubic points coming from the sporadic torsion and conjugates. And so we compute that the torsion on J1 of 21 is cyclic and it's of order 364, and we can generate it by the difference of one of these known cubic points and 3 times a rational cusp. And so we define an obligate Jacobi map. And what do? Well, we say for each multiple n of d, this n of d lies in the image of this obligate Jacobi map if and only if the linear system nd plus 3 infinity is empty. And because the curve is not trigonal, if it's not empty, then there's some effective divisor which it's actually equal to. And using Magma's intrinsic Riemann rock space, we can actually check and determine what this effective divisor is. And so we go through all of the multiples and we just check and we compute the complete list of n for which nd is in the image. And we just check that for all the values of n that we're getting, that these correspond to combinations of the known cusps that we have. And so this provably determines what all of the rational points on the symmetric cube of x1 of 21 are. So just to summarize, in joint work with Joseph Gunther, we conditionally bound the number of unexpected degree d points on odd hyperelliptic curves purely in terms of d using symmetric power Chabauty-Coleman. And we used tropical geometry to get explicit bounds when d is equal to 2 and 3. And in joint work with Martin Derickx, Anastasia Etropolski, Mark Van Hoeij, and David Zureick-Brown, we complete the classification of torsion subgroups appearing for elliptic curves over cubic number fields. So thank you all very much for your time and attention.